Hi guys, and welcome to the first in the series of videos on motion and energy. Now you know this topic is going to be focusing on you developing an individual research project for yourself where you're going to investigate a particular aspect of one of the sports that you're interested in. And so you're then going to look at ways of analysing the motion, looking at some different ways in which we describe motion. So to help you with that, this first video is just going to start defining some of the important terms. And here are some of them. When we're describing motion, there's basically a few important descriptors that we need. The first one is distance. So distance is basically just how far an object travels. Now, similar but slightly different to distance is displacement. And displacement is actually about the change in position of a particular object with respect to a certain direction. The difference between distance and displacement is probably easiest to see if you think about a circular running track. If this circular running track is a 400-meter track, then if you were to run around this track once, you would have covered a distance of 400 meters. But if you came back to the place you started from, your displacement would actually be equal to 0. And this is because displacement is a measurement from a starting point to an end point in a particular direction. So if you run around a circular track, you'll end up at the same place that you started, and hence your displacement is 0. You haven't gone anywhere from your original position, even though you've covered a distance of 400 meters. Time is another important quantity when we're describing motion, and that is just how long the object actually spent in motion. We tend to measure distance and displacement in meters, sometimes in kilometers as well. Time, generally speaking, we're going to measure in seconds. Now, time can also be measured in minutes or hours or days or years, but we're going to look at most of our measurements of time in seconds. Putting distance and time together, we get speed. Speed is basically the rate of change of distance over time. Speed is related to how fast an object is moving. And there are ways of calculating average speed where the average speed is equivalent to the total distance that you cover divided by the time it took you to cover that distance. For example, if it took you 40 seconds to cover the entire running track, then you would have covered 400 meters in 40 seconds, and therefore you would have been running at 10 meters per second. Similarly to the groupings of distance and displacement are the groupings of speed and velocity. Velocity is the same as speed in terms of its magnitude. That is, it's also a measure of how fast an object was moving, but it tends to specify a particular direction. So in velocity, we're actually looking at the direction of that motion, just as we did with displacement. And acceleration is the rate of change of velocity. So acceleration is equal to the change in velocity divided by the time. We can often change that to being the final velocity minus the initial velocity divided by time. But these are equations we'll look at a little bit later. To go into a little bit more detail about distance and displacement, we actually need to start understanding how different objects move. Because displacement compares the end position with the starting position, it is possible that we can have a very large distance covered and yet a displacement is equivalent to 0. With displacement, we don't worry about what's happening in the in-between movements. We don't worry about the whole of the motion. We simply look at the starting point and the end point. So if an object were to end up back where it started, then the displacement will always be equal to 0 meters. If the object were to travel 250 kilometers, but end up 1 meter north of its starting point, it would still have covered a distance of 250 meters, but its displacement would be 1 meter north. The symbol for, I guess, the only sensible reason is that distance already has the symbol d, is that the symbol for displacement is an s. So in this case, we would say s equals 1 meter north. Now, I know this is going to start getting a little bit messy when we start talking about speed as well, so we'll try and make sure that we keep these units consistent. SI is System International. It is an international system of units that is used around the world, and it means that different scientists in different places are always referring to the same things. And that means we can keep consistency and also share information between different scientists. A better way of explaining the difference between distance and displacement is to introduce two new terms to you. Those two terms are the terms scalar and vector. These are new terms because we haven't really looked at them very much in the past. There's not a lot of difference between these except that one has direction and one doesn't. Distance is a scalar quantity. This is because it only has a magnitude. It doesn't have direction. So I could say distance is equal to 100 meters. And that would be perfectly reasonable for distance. Displacement, on the other hand, is a vector quantity. And vector quantities have both magnitude and direction. So size, another word for magnitude, and direction. So displacement would be 100 meters east. Displacement must have a direction as well as a magnitude. So distance, just the magnitude, just the size of the distance, displacement, the size, and direction. Now this direction can be a compass point, often is, north, south, east, west, or some angle in between. Or it can also be left or right, up or down, and forwards or backwards. Sometimes you will see arrows to represent these vectors, but they are something we'll talk about at a later time. The key difference then is scalars have magnitude, while vectors have magnitude and direction. Some examples of scalars include distance, speed, and time, whereas some examples of vectors include displacement, velocity, and acceleration. One of the most important things that we are able to do is to describe motion from a graph. And I will give you a number of examples of graphs from time to time to help you to understand what is going on with a certain type of motion. If I was to give you a graph like this, then what I would want you to do is to highlight several sections from this graph. So at time 0, at the start, an object begins to be measured from a certain point. The section of the graph where there is a rise indicates motion. In this case, the motion is a steady or constant increase in displacement. Put simply, the object, the person, the ball, whatever it is that's actually moving in this case, is going north and has covered 4 meters in 6 seconds. So we could say that motion is in a north direction for 6 seconds, after which the object is 4 meters north of its starting point. And then what happens? Well, then we have a little section of the graph here. What happens here is for the next 2 seconds, the object remains 4 meters north. Put simply, after 6 seconds, the object stops moving. There is no further change in its displacement. It isn't walking backwards. It isn't getting further north. It's not going east. It is still at 4. So therefore, it hasn't actually changed in this region its displacement, and therefore we can conclude that it has stopped. At this point in time, it's probably worth you having a look at pages 196 and 197 of your Oxford Insight Science textbook. You can access that online through your My Campion app. And we'll start to have a look at our analysis of motion in the next lesson. Thanks for watching.